Okay, how are you? I'm happy to be here. Let me get my correct view here. So I'm David Taransky. I'm a Spring Advisory Architect, which means I am part of the Spring team. I'm a core committer on Spring Cloud Dataflow and related products in the ecosystem, mostly backend message-based distributed systems, which has been my experience through most of my career. And I also spent time with clients, so customer-facing position where I help clients use products like Dataflow and get the most value out of them, and through short-term engagements and POCs and the like. So I'm happy to be here to talk to you about Dataflow today. Looks like a lot of great content on this track, so glad you could join us. So what we'll be covering today is a brief overview of Spring Cloud Dataflow, or as we abbreviate it, SCDF. We'll look at architecture of both the Spring Boot applications that are built for Dataflow and the architecture of Dataflow itself. And then we'll talk about some common use cases that are well suited for Dataflow. And then we'll conclude with a brief demonstration, about 10 minutes, showing an event streaming sample. At the core, Spring Cloud Dataflow is really about enterprise integration patterns. So these are based on distributed message-based systems and patterns that have been developed and described in the classic book of the same name by Hope and Wolf. Some of the patterns are payload routing or message routing, filtering, message transformation, enrichment, aggregate, split, things like that. And while these patterns bring a lot of benefits to enterprise developers, such as logical and temporal decoupling, so we can separate consumers and producers with a publish subscribe architecture. So the producer doesn't know which applications or services are consuming its messages. And the consumer doesn't know where the messages are coming from. It just knows that when it gets one, it has to do its job. That's logical decoupling, which makes the architecture very easy to change and evolve over time. The temporal decoupling means the producer works even if there's no consumer there to consume the message. So if you have reliable messaging through a robust messaging middleware, you can publish a message and the broker will keep it until the consumer is ready to pick it up. So that's reliable messaging. So we get a lot of benefits from those type of features. But since we're talking about distributed systems, and these kind of challenges are the same with any microservices architecture, unpredictable traffic patterns being the number one thing, do we know that our system can scale to handle a 10x increase in data processing load over the average? How can we deal with network latency or even network outages? Maybe we can provide caching where appropriate, but then we need to make sure our cache stays in sync, and we have to have some type of expiration strategy to make sure that we're not serving up scale data. We can use circuit breaker patterns, things like that, to isolate from cascading failures potentially when there's network outages, or to fall back if a critical service is not available. We have to deal with schema changes. So when you have distributed applications, the producer of a message may update its schema, and that may break consumers, downstream consumers that are expecting another type of format. We have to to be able to deal with that, and also API changes that can affect our application as we evolve. So sometimes we need ordering guarantees. So if we're doing event-driven processing, can we guarantee, or do we need to guarantee, that we receive events and process them in the order that they were emitted? How do we guarantee that? If we have multi-threaded application or several competing consumers, that we have processed the events in the correct order, because sometimes can lead to inconsistent state if they come out of order. So we have to deal with those kind of things. And then data loss or message loss, we have to make sure that we do not drop any critical messages or data when we have failures. And then we have to think about consistency. So we know about eventual consistency, but a lot of times that will affect application behavior, and the business users have to know that the system's eventually consistent and what that looks like and how that might affect what they're doing as opposed to how their legacy systems work. And most of all, we have to ensure that our system doesn't get into a state that's eventually inconsistent. That can be bad. But if it does, we need strategies to roll back to the last consistent state. So these are all the challenges that we face. And fortunately, we have a Spring framework that can help to handle some of these challenges. And I'm going to look at a part of the Spring stack that's most relevant to enterprise integration and the types of apps that we would build for use with Spring Cloud Dataflow. At the core, we have the Spring framework. It's been around for over 10 years, and that provides dependency injection, the secret sauce for Spring, aspect-oriented programming, declarative transactions, and what I would call legacy integration or traditional integration, such as Spring JDBC, messaging, JMS, web services, MVC, and the like. So these were the traditional enterprise integration type of capabilities that Spring has always excelled at and is known for. On top of that, we have Spring integration, which is the embodiment of these enterprise integration patterns that are described in the book. So Spring integration implements those models and in a very robust way, and also provides a lot of enterprise integration adapters for the most common type of open source products, SQL, NoSQL databases, messaging systems, and various other types, web services, various other types of capabilities that are provided by the Spring framework or other Spring libraries on this level. Next to Spring integration, we have Spring Batch. So Spring Batch was a very robust framework that we've had for a long time that supports batch processing through readers and writers and steps and things like that to compose robust batch jobs. And importantly, Spring Batch manages the state of execution and the history of execution so that we can have a batch job that, if it, say, processes 1 million rows of an FTP file and it crashes in the middle because it gets some invalid data or something like that, or some problem with the job itself, we don't have to rerun the entire thing. We can find out where it last picked off, what was the last successful transaction, and restart the batch job at that point. Spring AMQP supports programming with Rabbit, gives you a very robust and simplified programming model for working with Rabbit. And Spring Kafka does the same thing for Kafka. Spring Data, of course, makes it easier to work with SQL and NoSQL databases using the common model and the repository model. that abstracts these things, and Spring Security. So there's more on this layer that I won't get into here, but these are the main kind of core components. On top of that, we have Spring Boot, which of course makes it easier to build and package microservices using auto configuration for a lot of these products. And on top of Spring Boot sits the Spring Cloud family of products. And here we're going to look closely at Spring Cloud Stream and Spring Cloud Task. Spring Cloud Stream abstracts the messaging middleware. So it's made for messaging applications, and it really exposes functions, Java util functions such as suppliers function and consumers. And if you declare a function type as a Spring Bean, Spring Cloud Stream through its boot dependencies called a binder, and we have Rabbit and Kafka binders, Kafka Stream binders, and others that are provided by the community to really support any type of messaging middleware. Spring Cloud Stream will automatically bind that function so that the output of a source of a supplier function will pass on to a Kafka topic, say, and the function will have inputs and outputs bound to Kafka or messaging resources. And if you have a consumer, that will act as a sink, which will consume a message and do something with it. It will consume it off of a Kafka topic. Spring Cloud Task, that provides a model for task execution. And a task is any finite workload so that it does its processing and then will either complete or fail and then exit. So Spring Cloud Task provides facilities for tasks which are built with Spring Batch most frequently, but don't need to be. They can be built without Spring Task as long as they have a logical conclusion that they can mark as complete or they fail. So this is the architecture that we would use to build applications that work with Spring Cloud Dataflow. And so when we talk about cloud native enterprise integration, again, we will focus on Spring Cloud Task and Spring Cloud Stream. And so for Spring Cloud Task, again, we are talking about short-lived microservices that do batch data processing or some type of finite task. And these are built with Spring Boot and Spring Cloud Task, and they can be deployed to Kubernetes as job or Cloud Foundry as tasks, or locally as just JVM processes. And so typical use cases would be scheduled jobs where you want to run a daily batch process or hourly or weekly or monthly or yearly, any type of schedule, or more complex schedules. We don't provide scheduling per se, but we have some rudimentary scheduling that we delegate to the platform, whatever capabilities it has. So scheduling is outside by commercial products that support complex scheduling, but we can support a simple type of scheduling fairly easily that integrates with Cloud Foundry or Kubernetes. And scheduled jobs may perform some type of data migration, reading from a file, for example, and cleaning the data and storing it to a SQL or NoSQL data store. ETL is a related and common type of use case for tasks. Dataflow is very good at event-driven ETL. So let's say we drop a file into a directory. We have a source that is monitoring that directory and can pick it up and say, oh, we have a new file now. So we can go ahead and run the whole stream, but the core of the work would be done by a batch process. So again, for a large file, we'd want to be able to audit the execution, manage the execution, and be able to restart the job if necessary. So we would use Spring Batch to do the actual processing of the file, but we would have a stream that would monitor the directory and create an event when a new file is available, and pass that to a task launcher sync, which would launch the task using Dataflow that would perform the work. So this is a very common use case we see. And then again, if we're talking about machine learning, offline model training is a major use case that involves large-scale data sets as they come, that may be processed daily to retrain the model, refine its the model with more data. So when we look at Spring Cloud Stream, this is for an infinite, quote unquote, stream of data. We're talking about event-driven microservices that stay up and are always ready when an event happens. So we can process Twitter feeds, we can process HTTP requests as they come on demand for real-time processing. And Spring Cloud Stream applications work through a message broker. So we have a source, 0 or more processors in between, and a sink. So Stream always starts with a source and ends with a sink. And the data flows through that stream and will communicate via message brokers. Again, with Spring Cloud Stream, the apps themselves need not know about the message broker or which message brokers are using. They just implement a function that outputs to the message resources is as configured, but it's not part of the application code. It's all abstracted. So common use cases for streaming pipelines are any kind of enterprise data integration, as we've talked about, using these patterns. So very good for messaging integration. Event-driven architectures in particular, where we're using these publish subscribe type systems. It's very good for those type of event sourcing or event-driven architecture. And real-time predictive analytics, such as IoT type processes, where we'll see some example of that in the demo to follow. So Spring Cloud Dataflow takes these applications that are developed with Spring Boot, and itself is a Spring Boot application, but it doesn't really do anything at the runtime. It just is in charge of orchestrating these applications and then deploying them. Once the applications are deployed, they don't really need Spring Cloud Dataflow. If Spring Cloud Dataflow comes down, the applications continue to run, but Spring Cloud Dataflow gives you a nice development experience for monitoring the state of these applications, orchestrating stream and complex tasks, and deploying or undeploying, upgrading, and rollback for these applications orchestrations. Also provides dashboards for metrics, performance metrics through Prometheus or other metrics libraries, and provides admin consoles for task and batch execution status. So we have a graphic here that's showing on the top, the graphical editor, which is part of the Dataflow dashboard for composing a streaming pipeline and deploying it. And then at the bottom, we see this task composition, which can be fairly complex and is run by something called a composed task runner. So we can launch these batch jobs, composed batch jobs, and track the execution by each application. Along with Spring Cloud Dataflow itself, we provide a number of prepackaged applications, dozens of these. Here's a partial list and growing. most of what we do is on the source and sync side, and we integrate with common open source products. So we have file FTP, SFTP, of course. We can provide change data capture through the open source Debian library. We support, of course, Apache Geode. HTTP can provide a source, or JDBC databases. We can pull databases and create an event whenever a data set is changed. JMS source can process mail. MQTT for IoT. NoSQL data sources such as MongoDB and S3. And we can process messages from an external Rabbit cluster and so forth. We have some Twitter capabilities and WebSocket sources as well. On the sync side, we can store to various sources, various data stores like Cassandra, MongoDB, and JDBC, or Gemfire Grid. And we can also create files or create FTP files. We can route the output of a stream to another stream. We have a task launcher, a sync that uses Dataflow to launch a task that's registered in Dataflow. So when we get an event from a stream, we can use that to trigger a task. We could also tweet messages or update Twitter by syncs and do asynchronous I/O through our socket or WebSocket. So a bunch of capabilities for integrating these things. On the processor side, we provide some generic types of aggregators, filters, scripted type of process, and spell expressions with transformers and filters to do some basic common things. But most often in a while, we see where developers write their own processors, which really perform the business logic that's needed for their business domain. Of course, all our prepackaged applications are published and available in our Maven, GitHub, and Docker repositories. They're open source at GitHub on Spring Cloud Stream Applications repository, and they're well documented on our Dataflow site at dataflowspring.io. So looking at the Dataflow architecture, basically we deploy two servers, Dataflow server and Skipper server, and these are each backed by a database, it's a SQL database. And Dataflow embeds a web dashboard, which gives you a rich GUI client for performing these type of orchestrations and related tasks, and also a command line shell, Dataflow shell that has a CLI type interface that can be done on a terminal session, or can be used to can ingest scripts that are written in shell commands. The Dataflow server itself does several functions, such as registering applications, storing stream definitions, and things like that, being able to deploy and undeploy tasks. For deploying streams, we have a separate server called Skipper, and Skipper keeps track of manifests for stream versions and allows updating and rollback for CI type of operations on streaming applications. And it again keeps the state of stream deployments and various versions of stream manifests in its database. So we can deploy Dataflow on any platform, most notably Kubernetes, Cloud Foundry, platforms like TAS, or we can deploy it on your local machine, which is good for development, but we don't recommend this for production. For Kubernetes, we can deploy in any Kubernetes cluster, GCP, Amazon, TKG, or Minikube. it really doesn't matter as long as we have a Kubernetes dial tone, as they say. Dataflow can run on that, and has for a long time. We have a common deployment model, so we are able to accomplish this through a service provider interface called Spring Cloud Deployer, which abstracts these type of deployment operations. So we're able to use the deployer SPY to deploy, undeploy, and upgrade, rollback at the stream or application level. So one benefit of Dataflow is you can really manage these applications orchestrations as logical units. So you can see which applications are related. If you look at applications on these platforms, so if you look at Kubernetes pods, for example, you may see a whole bunch of streaming applications, but you don't really know a priori from looking at that which ones are related or what the dependencies are. So Dataflow gives you a unified view of all that. The deployer abstracts these applications. So when we say deploy, if we're talking about a Kubernetes deployer, then it's going to create some Kubernetes YAML. It's going to create a deployment or a stateful set along with some pods and services and things like that. Kubernetes resources needed. For Cloud Foundry, it will create an app instance or task instance, whatever it's called for. And for local, it just creates an external JVM process. So all these things are abstracted away, and Dataflow can handle any of these environments. Dataflow also provides a domain-specific language for orchestrating stream and task pipelines very easily. That can be used in conjunction or in lieu of the graphical editors that are provided by the dashboard. So the Dataflow clients, such as the dashboard and the Dataflow shell, are backed by a robust REST API. Some of the operations are shown here. There's a lot of them. So the web dashboard uses this API to talk to the Dataflow server. And likewise, so does the cell. We also have a Java DSL, which gives a high-level Java builder for building these types of orchestrations, and that delegates out to the API. There is a Dataflow template that is based on Spring REST template, so it wraps the REST template to give you an easy Java API that you can use to write custom Java clients, or you can write a custom client in any language that can hit these REST endpoints. So a lot of flexibility there. Spring Cloud Dataflow is part of the Tanzu application suite, and there's a pro version that's focused on Kubernetes. And in addition to getting great support from VMware, we also provide some additional features. One of them is multiple input and outputs on the UI. Spring Cloud Stream supports multiple inputs and outputs out of the box, and you could compose those yourself using Spring Cloud Stream. But if you want to do it with Dataflow, you would need to upgrade to the Pro version. And here you see an example of the DSL in the text window up above, which for this fairly complex orchestration. We also have alerts where we can monitor the repo wherever these registered applications are. And if there's an update, it'll notify the user that updates are available and can even automatically update the streams to the latest version. So that's a pro feature. So we're looking at how we can get more value from, or users can get more value from purchasing the pro license. So as far as resources go, we have a really nice website that has a lot of different examples and recipes for Dataflow. It shows you how to get started with Kubernetes or any of the other platforms, and provides a lot of documentation for the out-of-the-box stream applications, et cetera. So this is the portal, the starting point for anything Dataflow related, Dataflow Spring IO. For the commercial product, there's a link to Dataflow Pro, which is still in a docs pivotal IO domain. And the demo code that we're about to see is in my repo for Spring 1 2020. I stole it from Sabi's demo at Spring 1 2020. So thank you, Sabi Anandan, who's the product manager, for providing me the core of the demo. So the demo is actually an IoT type of simple example where we would have a fleet of trucks and we're monitoring sensor data. We're capturing the sensor data through a source, and we're looking at various metrics such as internal temperatures, external temperatures, and brake temperature. In this case, we're going to be processing the brake temperatures, and we're going to use Kafka streams to do some stateful stream processing where we'll aggregate and compute average brake temperatures over 10-second windows, and every 10 seconds we'll emit the average by each truck, which is identified by its vehicle identification number. So with that, I have a pre-recorded demo, so I'm going to stop the presentation and show the demo. We've deployed Spring Cloud Dataflow on Kubernetes, and we could have deployed it on TKG cluster or Amazon or Google Cloud Platform, any Kubernetes cluster, and Cloud Foundry platforms such as TAS. In this case, we're running on Minikube, and we can see the Dataflow components running as we discussed earlier: Spring Cloud Dataflow Server, Skipper, the SQL database, and we also require the message broker to support our applications. In this case, we're running Kafka and Zookeeper to support Kafka. Let's take a look at our application source code. And here we have a simple Spring Boot application, which is going to be our source today. So we are monitoring a fleet of trucks, and since we don't have a real fleet of trucks, we're going to emulate the data using random values, and we're going to set certain temperature readings. The velocity, acceleration, and the ID will be drawn from a list of canned vehicle identification numbers. You'll notice this application doesn't have anything about Kafka or messaging or streaming. The key component highlighted here is a Spring Bean, which is declared type supplier of truck. So it's a function that will return an instance of a truck every time it's invoked. Spring Cloud Stream is declared in the POM as a dependency, and we'll use Spring Boot auto configuration to automatically set up the Kafka binder and bind the output of this function to a Kafka topic in this case. And that's going to feed to our processor, which is called the brake temperature application. And this one's a little more interesting. This uses the Kafka Streams API to do advanced stream processing, stateful stream processing. It provides a rich set of features such as windowing and grouping, aggregating, which we want to use here. So we're going to group the data that comes in, which is a K stream, Kafka stream of trucks, and we're going to output a stream of average brake temperature accumulator, which is just a POJO we're using to store the average brake temperature and the metadata used to compute it. The function itself will use the vehicle ID and set it as the key value. It'll group by that value, and will window every 10 seconds. It will aggregate over the break temperature values uh, and group them by each vehicle identification number. So we'll get an average over 10 seconds, which we can use to monitor the temperatures of these trucks. We'll just feed the output of this function to a log, which will use the standard Spring Cloud Stream log sync for Kafka. So let's go back to our data flow view. And we first need to add some applications. We currently have no applications registered, so we can use register one or more applications. So we're going to manually register the source, which we wrote. We'll call it trucks. Type source. And we have packages as a Docker image, which is required for Kubernetes. And we can use the break temperature application as our processor. And again, it's a Docker image. And for the sync, we're going to just call it log, and we will use the prepackaged application from Spring Cloud Stream Docker Hub repository. And we'll import those. And now we've registered them, and that simply tells Dataflow where to get the bits when we have to deploy the apps. So they haven't been deployed yet, but we will create a stream with them. And we're using the stream editor. It's provided by the dashboard, and in this case we only have one source, one processor, and one sink. We can drag them out and can connect them up. And as you can see, the text window here is showing the stream definition language. Very simple in this case. We have a truck source, a break temperature processor, and a log sync, and the pipe symbol indicates that the output of trucks is going to go to the input of break temperature over the messaging middleware configured for these applications, Kafka in this case, and the break temperature is going to output to the log. So we can create the stream, and we'll call it average break temperature. And great, it likes the name. And so we've created a stream, and it shows as undeployed. So we can use this available actions to deploy the stream. And in this case, it brings up a deployment properties sheet where we can set properties on each one of these apps, such as platform information, the memory, CPU, disk configuration. We can set various properties that may be provided by the application itself. We can change the versions if we want, or we can, do a variety of things. But we're just going to use the defaults in this case, and we'll go ahead and deploy the stream. And Dataflow server picked up our request and said it received it and it's working on it. So we're still deploying. So if we go back to our stream view, we can now see 3 additional applications that we've just deployed on Kubernetes as Kubernetes pod, and they're showed as running. And we're interested in verifying that it's running. We can look at the logs for the log sync. And in this case, it's still starting up. But when it starts up, we should see the break temperatures coming across as we tail the log here. So here it comes. So we see the break temperature along with the other metadata that was defined in our accumulator class. And these are windowed over 10 seconds. So for a vehicle ID, the counts may go up and down as we go. So if the stream is running, it takes a little while for the liveness and readiness probes for Kubernetes to set these apps as ready. When they do, the application that was shown as deployed in Dataflow. So rather than wait for that, we will just go ahead and undeploy the app. If we undeploy the stream, it's going to undeploy all three of those applications. So we're able to deploy and undeploy at the stream level, at the logical level of our application. Once we undeploy the stream, we can take a look at our Kubernetes, and we can see they're terminating and the pods are gone, freeing up the resources. So that's the end of the demo. Thank you. Okay, so that's concludes my talk. Have there been any questions or anything?
No, I don't see any questions in the QA. I think you explained it all very good. So there were no questions open.
I explained it too well. That must be it. They didn't defect to the infrastructure track, did they?
No, David, thanks a lot for presenting with us and doing this.
Thanks for having me.